Hello and welcome to the new session of new video, how to read a character table part 1. Actually, we have described the methods of constructing character table in various videos earlier also. But I would suggest you to go through this video as it has some information that collectively is very important for those who are the beginner in this field and those who are the experts in this field. For both of them, this has a worth looking video. So let's go for our new session, that's how to read a character table, and I'm your instructor Saurabh Bhaktibodh. I believe that numbers also have characters, and in the character table these numbers have to be decoded. But then from very basic and fundamental question that comes in your mind is, what is a character table, isn't it? And the chemistry students learn to develop a character table with or without using complex mathematical functions. But the question is, what is this character table? Ultimately, we have to understand and how to read or understand it. That's the question, of course. And is it as simple or complex as to read in horoscope? Say, for example, the Pandits of India, the astrologers and Jyotishis, they understand their tables quite well. Is it that easy to understand the character table? And we are familiar with our character table. It looks like an horoscope also. At some point of time, you see the point of the molecule, then the symmetry elements, then the symmetry labels talking about irreducible representations, then there are characters, then numbers, then there are some basis functions, etc. So what it is and how is that important? And if we understand the components of character table, how to draw inferences for chemistry applications? I don't know. What does it mean? A character table, what the hell it is? Well, yes, this is how a mind gets occupied when you look about a character table. We know that the molecules that have been classified into various symmetry properties, like males and females we have. Similarly, molecules have peculiar characteristic point of, like for water it is C2V character table, and for other one it is a tetrahedral molecule. And we understand that if we talk about water molecule, it has a peculiar C2 point group that has 4 components, 4 symmetry elements, including identity, as E, identity, as C2, sigma V, and sigma V dash are the 4 symmetry elements of this point group. Then each symmetry operation can be represented in the form of matrix corresponding to a Cartesian coordinate system. Thus, we have a set of matrices now. So, matrices have actually the information that is in a coded form when a particular operation is carried out, and this coding would be very important to generate informations. These matrices can be decomposed to smaller dimensions using a method called similarity transformation technique. So matrices can be decomposed into smaller components using one simple mathematical operation, that is similarity transformation. And once if we are able to do it, then those matrices which can be decomposed are reducible matrices, while those which cannot be further decomposed are the irreducible representations. Look at here. Here, let us believe that this is a 3x3 unit matrix, and if by some means, that is so-called a similarity transformation method that we have described in earlier videos as well, if it is possible to decompose into a smaller dimension and further into a one dimension, so the 3 dimension can be decomposed to a 2 dimension and can be 1 dimension respectively, then these matrices are reducible matrices. However, this matrix, which has only one component, cannot be further decomposed, so that is known as the irreducible representations. So a 3D can transform into 2D and further by 1. This kind of transformation is mathematically possible only using some techniques. And that technique is similarity transformation, as I have described. See, for example, there were 3 by 3 rows and 3 column matrix, and if it is possible to just block diagonalize, so this is actually a 2 by 2 and 1 unit matrix. So this similarity transformation is such that C inverse AC is equal to B, and C inverse 0, of course, identity. But then these operations give a new result. So as we have seen that a matrix that cannot be further reduced or further decomposed is irreducible representation. Is it the important component? Yes, it is the most important thing. They are of fundamental importance, and they can be of 1 dimension, 2 dimension, 3 dimension, etc. And this actually determines the dimension of matrix, which cannot be 0. You cannot have a 0 order matrix, and you cannot have a fractional order matrix as well. You cannot have a matrix of order 1.2. So it is either 1D, 2D, or 3D, etc. And they can be obtained by matrix manipulation. Now, how we have a basis for character table? Because a character table is a collection of characters of irreducible representations of a particular point group or a particular point group. Now, the next point that needs to be understood is then what is character? And the answer is simple. A character is simply the diagonal sum of the elements. If here these are three matrices, maybe they may be reducible or irreducible and so on. But if we just go for their diagonal sum, this has got a diagonal sum of 3, this has got a sum of 0, this has got sum of -1 plus 1, that is 0 and -1. So the characters are 3, 0 and -1 respectively in these situations. So we must clearly understand that a character is nothing but it is the sum of the diagonal element of any reducible or irreducible representations. Now, if you have got this, let us again look at what we call as a character table. So, on one side you have point group, other side you have notations for irreducible representations. From where they have come, we will discuss them. This is a very important thing. These are symmetry dimension operations, and the 1, 1, -1 and so on, they define the characters. The fourth and fifth column that gives the basis function x, y, z, rx, ry, rz and the binary products that we'll understand or we'll try to understand in the part 2 of how to understand the character table. Now, to construct a character table, what we generally know, the point of the molecule, like for example C2V for water, and what we do not know, of course, the number of irreducible representations, their dimensions and their characters. These things are not known to us. So there are only two things that are known to us: a molecule with a point group and the symmetry properties of that. And to know this, what is required? Matrix representation for every element of that point group. It's decomposed into smaller dimensions to obtain its corresponding irreducible representations, and then we have to find out their characters. And is it going to be cumbersome? Is it going to be very problematic? Is it going to be very tedious? Yes, of course. Yes, of course. If you don't have any adequate knowledge of matrix algebra, this is going to be very complicated indeed. But then, with dear students, the great orthogonality theorem is there. We have fortunately the great orthogonality theorem, which assists us to draw or to make a character table without actually constructing the matrices. And remember the great orthogonality theorem that we have discussed earlier, but it was, the properties of irreducible representation. It was referred as the properties of irreducible representation. Here we are referring as the great orthogonality theorem, though both of them are the same things. Well, now what? If we know this, we can be in as comfort as the man in this sketch. So, the great orthogonality theorem, and let's try to understand what are its components and how it is used without actually devising, constructing matrices, decomposing them and all of that. So there are 5 important points, and let's start one by one. Point number 1, the sum of the squares of the dimensions of irreducible representation of a point group is equal to H. H is the total number of symmetry elements in operation that a particular molecule does have. So the square of the dimensions is equal to the order of group. This is rule number 1. If L1, L2, L3, etc. are the dimensions, then the square and the summation should be equal to the order of group. This is the rule number 1. Rule number 2 states that the sum of the squares of the characters of irreducible representations of a group is also equal to H. So chi I square is equal to H. Chi1 square plus chi2 square plus chi3 square plus and so on is equal to H. Chi1, chi2, chi3, etc. are the characters of irreducible representations. This is rule number 2. This is about the characters. Rule number 3, the most important component of the great orthogonality theorem is the vectors whose components are the characters of two different irreducible representations are orthogonal. That is chi I r into chi j r, and their summation over entire operation r has to be equal to 0. So where the character of ith irreducible representation is chi I r and chi j r is a character of jth reducible representation corresponding to the same operation r. So this is the most important guideline for the great orthogonality theorem, rule number 3. Rule number 4 and 5 are fairly simple. Rule number 4 says that in a given representation, the characters of all matrices belonging to the operation in the same class are same or identical. So characters of the same class are same. That is rule number 4. And the rule number 5 states that the number of irreducible representations in a group equals to the number of classes in that group. This is the most important thing. How would you decide that a particular point group have these many numbers of irreducible representations? Of course, by just looking at number of classes. So number of classes is equal to number of irreducible representations of that particular point group. So having the 5 postulates or 5 points of the great orthogonality theorem, it's quite easy to understand the character table, to make it, to construct it, and so on. Now, a very important thing that you should note that there is a different scheme of nomenclature as proposed by R.S. Millikan for irreducible representations is based on certain rules, certain assumptions, and they are as follows. So please note them very carefully so that you will be able to understand the various character tables. First thing, one-dimensional irreducible representations are either given by A or B, two-dimensional irreducible representations are denoted by E, and three-dimensional irreducible representations are always denoted by T. 1D is symmetric with respect to rotation, that is, the principal axis are indicated by A, while if they are antisymmetric with respect to principal axis, then they are determined by or denoted by B. So this is the difference when to use A, when to use B. We should use A when the characters for principal axis if are positive, then we say that it is A. And if the characters for principal axis are negative, then we say it's B. That it has undergone a transformation. Similarly, sometimes we give a labeling of different kinds. So sometimes we get A1, B1, A2, B2, etc. So symmetry with respect to C2 normal to Cn or to a sigma V is indicated by the subscript A1, B1, etc. Antisymmetry is indicated by the subscript 2, and sometimes it is like A2, B2. So for symmetry with respect to a C2 normal to Cn, so if we are talking about the character for C2, then A1, B1, A2, B2 terms can be used. Symmetry with respect to sigma H is indicated by primes A prime, while antisymmetry is indicated by double prime. So symmetry with respect to sigma H is indicated by primes A dash or A prime, or antisymmetry is indicated by E double prime, E double dash, and so on. Symmetry with respect to center of inversion I is indicated by G, that is EG, or antisymmetry is indicated by U, garret or ungarret, G-red or unG-red, as whatever you pronounce it. So it is AG, EG, AU, BU, etc. E and T require some more labels, but they are not quite easy to assign. Where you have learned that in crystal field theory, the d orbital splits into EG and T2G set of orbitals. Now that you can see that E stands for doubly degenerate and T stands for triply degenerate set of atomic orbitals. Sometimes it is quite easy to understand that the character of +1 indicates that the basis function has not been changed as a consequence of symmetry operation, while -1 shows that that particular basis function has reversed. That is, x has gone to -x, y to -y, and so. And the character of 0 indicates that the basis function has undergone more complex changes. So that is sometimes, quite not easy to understand. Now, I'll just examine a few character tables, say C2H point group. So if you talk about C2H point group, you see that there are the characters, the total symmetry elements are 4, 1E, C2, I, and sigma. There are 4, order of group is 4. Number of classes, they belong to each different class. So number of classes are 4, and therefore there will be 4 set of irreducible representations. Now you just look at here, total irreducible representations are 4. All of them are one-dimensional. A and B are, of course, terms used for one dimension, and the character of identity is equal to always dimension. So because they're one dimension, the character for identity would also have 1 each. So this is 1, 1, 1, 1. This is 1, and this is obtained by squaring the characters of the first row. That is also +1. The rest of the elements can be filled according to the orthogonality concept, that the net result should be 0. So there should be 2 +1s and 2 -1s. So and that's how we can generate this particular character table. You can also verify the orthogonality. Take any two irreducible representations and you'll see that their product has to be 0. Now the question is, why AG and AU notations, not A1 and B1? Because here we are talking about I is there. So if it is symmetric with respect to I, the characters are positive. If it is antisymmetric with respect to I, the characters are negative, and therefore AG, BG and AU, BU terms have been used here. Talk about ammonia molecule, which has a C3b point group. It has the 6th number of operations, so order is 6, and number of classes are 3. So identity is one class, C31, C32 is in one class, and sigma B dash, and sigma B double dash, sigma B prime, sigma B double prime, they belong to the same class that we have studied in earlier videos also. So there are 3 classes, and as a consequence there will be 3 irreducible representations. They have been denoted by A1, A2 and E, one dimension, and 2-dimensional irreducible representation respectively. Then you can also verify the orthogonality, and you just notice here that we have used term A1, A2, E. We have not used term A, B and E. We could have used it, but because the characters are positive with respect to rotation in both the cases, I would not use the term B Instead, we are using A1 and A2, etc. because they are negative only with respect to the vertical plane. So that's why A1 and A2. Similarly, you just refer to a point group D3H. It has as many as 12 number of symmetry elements. There are 6 classes. Then there are irreducible representations indicated by primes. A1 prime, A2 prime, E prime, E double prime, and so on. You can understand that why we have used for C2, because C2 is negative here. Then we are using the term primes for A1 dash and A2 dash to differentiate them, and so on. And the rest of the things, that is orthogonality. Yes, and of course one more thing. E is a two-dimensional irreducible representation, so its character is 2 here and here also. The rest of them are one-dimensional, so you have 1, 1, 1, 1, and E for E there are 2. So you can just assign it, you can verify orthogonality, and notice why primes don't be on B2, etc. You can find yourself. Tetrahedral point group has a very peculiar 24 number of symmetry elements, symmetric number of classes being 5. So there are 5 number of irreducible representation: A1, A2, E, T1, T2, A1 one dimension, A2 again one dimension, E 2 dimension, T1 and T2 are respectively 3 dimensional representations. And you just notice that this is 1, this is 1, this is 2 because it's 2 dimension, this is 3 because it's 3 dimension, this is also 3 because this is 3 dimension. The rest of the first row characters are 1. That is quite obvious to understand. And similarly, the octahedral point group you also work out for yourself and try to understand the orthogonality concept here also. So this is how you can talk about the character table in a part. In the next part, that we'll talk about the remaining things that are very important again. But then before winding up the work, we have to describe the summary. So a character table has the following components. First, point of the molecule. Number 2, symmetry elements and operations. Number 3, classification of symmetry elements and operations and their classes. Even if you don't know about it mathematically, you can just by observing, you can find out the classes. Number of classes gives number of irreducible representation. Rule number 5, the great orthogonality theorem. Dimensions can be obtained by the rule 1 of the great orthogonality theorem. The sum of the squares of the dimensions equal to order of group. Once dimensions are decided, characters are identified for 1D, 2D, 3D, etc. for identity, and other characters can be used from the orthogonality concept rule 2 and 3. So this is how we can use the character table and understand the component. Thanks for watching, dear friends. See you in the next video.